Now, one other thing that's kind of useful here to talk about when we understand how to find the concavity and inflection points of a graph is to notice, like I can see here back on what we left off with in example 6, is that if I already have determined where a graph is concave up or concave down, which you can see here by my negatives and positives, as well as this green portion of the curve that I've roughly sketched, then we can see something kind of interesting. Take a look here at this piece. I know that my graph is concave down here, but since it's concave down, doesn't that mean that there's going to be on that picture a local max somewhere over here below 0? And actually on this part, if this graph is concave up, then doesn't that mean there should be a local minimum somewhere here in between 0 and 1? And similarly, there should be a local minimum over here, somewhere off from 1 to infinity. So I can see that by understanding the concavity of the graph, there may actually then be a way to determine if there are mins and maxes. So this is what we're going to summarize into what we call our second derivative test. Both the first derivative test and the second derivative test were concerned with attempting to find where local mins and maxes occur. Let's take a look at what this theorem says. Suppose that we calculate our second derivative. We recognize that it's continuous near a point of C. If it's the case that our first derivative was 0, that is, we have a tangent line of slope 0 at this critical point, and if it's the case that our second derivative is positive, meaning again that it's concave up, well then wait a minute, that looks just like this picture. I have a graph that's concave up, and there's a tangent line of slope 0 I could imagine drawing in here. Well then this function would have to have a local minimum value at C. And it's the same way, just in the reverse order, for the second part. If I have a tangent line of slope 0, and I have concave down, the second derivative is negative, like this, then that would correspond to a highest point on the graph, and so I would end up with a local max. So let's take a look at how we could actually use this to help answer question number 7 here. I want to use this second derivative test to find all the local extrema for this graph f of x. All right, so let's go ahead and actually try to compute this. So first off, I'll state that we calculate. And again, we know we're going to need f prime of x and f double prime. So this is going to be 15x to the 4th power minus 15x squared. Okay, now I can go ahead and calculate my second derivative. This would be 15 times 4 is 60x to the 3rd minus 30x. And notice again, I could rewrite this probably a little bit. It looks like I can factor out a 30 as well as an x, and I'd be left with like a 2 x squared minus a 1. Is that what I'm going to end up with? So if I end up with this, then I can go ahead here and start to see a couple different things that can start to play out. So first off, I'm going to go ahead and start to try to figure out where my first derivative is equal to 0, and also then where my second derivative is going to be positive or negative. So first thing I need to check here is ultimately, when is my first derivative going to be equal to 0? So to do that a little bit more easily, why don't I factor out what I have up here as well? Looks like I can take out a 15 and an x squared. That would leave me with an x squared minus a 1. So this could be rewritten one more time as 15x squared x minus 1, x plus 1. So I'll note this. I'll say we see that f prime of x is equal to 0 when, and I can just take a look right here. This would be when x is equal to 0 or plus or minus 1, right? Any of those values would make the first derivative equal to 0. So now I know these are, again, potential spots where I might have mins or maxes. But the second derivative can help me determine this by just taking a look at what happens with these particular values inside of my second derivative calculation. So I'm going to go over here and I'm going to think about what happens, and I'm going to set up a little table here. So I kind of have my values of x that I'm going to be working with, my values of f prime or f double prime of x, and then ultimately I'll state here what I can state ultimately about my conclusion. Okay, so let's see what we have. I have x values of -1, 0, and +1. So let's see what happens if I was to plug -1 here into my second derivative. Now, if I was to do this, it doesn't matter which form I plug it into. It's actually going to be pretty easy even just to plug into this form right here. Notice I would get -60 plus 30. So my second derivative here would actually come out as -30, indicating that I got negative. My graph is concave down. But if at x equals -1, the graph is concave down, then the second derivative test tells me that there should be a local max at x equals -1. Specifically, I could calculate f of -1 by plugging -1 in here. Notice that would get me -3 plus 5, so that should get me a value of 2. There's a local max at 2. Now what happens if I plug in the value of, say, 0? If I plug 0 into my second derivative, notice I just get back the value of 0. Now, the second derivative test doesn't tell me anything about what happens if my second derivative spits out the value of 0. So what I'm going to write over here is just inconclusive, meaning that I don't really know anything about what happens at 0. I can't figure that out. The second derivative test doesn't tell me if I do have a max there or if I don't have a max there. It doesn't tell me anything. I'm kind of stuck. Now, if I plug in the value of 1 here into my into my second derivative, notice that I'm going to get 60 minus 30. That's going to get me a value of 30 overall, which definitely means that my second derivative is positive. So my graph, again, is going to be concave up. And if a graph is concave up, that's going to produce a local min. So there's a local min when x is the number 1. And of course, if I plugged in the value of 1 in here, I could easily see that I get back the value of -2. So all that the second derivative test here is going to help us do is to find some local mins and maxes in a way that's different from how we used the first derivative test. Now, most of the time, I would actually say that the use of the second derivative test is not going to be very frequent. It is very rare that we're going to need to go through all of this work when, if you noticed here, we already found the first derivative. We already factored it out. We could have put these critical points on a number line and just found our pluses and minuses and immediately determined the result. We would have found out, again, even what happens at 0. We would have not had inconclusive, but we would have had a definite conclusion. So the second derivative test is not all that important in every situation. But you could see that maybe if I knew the second derivative of a function, or if I knew something about the second derivative of a function, that may actually be helpful in determining what's happening with mins and maxes. And this actually does become of particular use in much later calculus courses, and specifically in Calculus 3. This idea gets used a lot when you start to work with functions that have multiple input variables.